Has anybody used like oversampling or undersampling, like throwing out data from the majority class or oversampling stuff from the minority class?
Yeah, I've done it all. And
Yeah.
it seems like Chicago over the years, they eventually just go to some version of focal loss. It seems like they just leave the data as is without oversampling or undersampling, and they just change the loss function. And that kind of shifts the class imbalance problem from your training data to your learning algorithm. That's the trend. From
Mhm.
my experience, that seems to work the most efficient from what I've done.
So, welcome to chapter 3 of designing machine learning systems. Yeah, so maybe before we jump into any particular section, if anybody wants to give like a high level response to this chapter, which is on training data, sampling it, getting a hold of it, labeling it, and deciding what those labels should be, and what to do when you don't have labels, how to handle class imbalance, and then data augmentation to handle if you don't have enough classes. So these sort of like once you've solved those data engineering problems that we talked about last time of just how to hold on to the bits, now you have to worry about like how to make those bits useful for machine learning, and that's sort of the theme of this chapter. Are there any sections anybody like really liked, really hated, anything like that?
I can give just a quick kind of thing that really stood out to me, that a lot of the stuff here is I keep coming back to sampling. Everything that you do in, finding validation sets, or, when do you actually trust your model to go out in production, kind of everything ends up coming back to sampling and the theory behind sampling. So
Mm, mm,
this is something that I can keep coming back to and learning more about, just because like if you trust your validation set, you can kind of build and move faster, but getting
mm,
there is
mm.
actually quite difficult. So I really like all these, like, labeling, all the sampling theory that Chip goes into here, because I think it's really at the crux of all the stuff that we do in production. So I really enjoyed that part.
Awesome. Yeah. Do you want to comment more on that? I have thought of sampling my past as like a research scientist, not even in ML, like thinking about
Hmm.
sampling in biology and psychology, but I haven't really thought of it since doing machine learning, because I mostly think about these things, I don't know, like like Common Crawl or or ImageNet, where
Right.
like it's such a big sample that people don't necessarily think about the sampling that much, and it's also done by somebody else. So I'd love to hear more about like how sampling has come up in the work that you've been doing.
Yeah, I think for me the biggest thing is, so yeah, we do like computer vision analytics with traditional security cameras, and they're everywhere in the world, and they're all kinds of different resolution and all kinds of different quality of cameras. So really the input stream that comes into your model is quite different. So how do you build a data set that actually represents that universe, that doesn't take 10 hours to run on a validation set, that actually gives you enough confidence that you see that result and you're like, okay, this model is better to go up in production. So
Mm,
building that still is something that I work on all the time, just to, yeah, how do you get that representative sample of something that's doing like 200, 300 million predictions a night,
yeah.
and that doesn't take days to run a validation set, and that sampling theory and really understanding, like, I think we were talking about this or some people were talking about this in the computer vision Discord, but
Mm,
uh, how do you quantify, like, features of images, and can you answer that this is a representative sample of images, that then you're going to put this model in production, and it's going to be better than the one you had before.
yeah.
That's kind of the way I always end up coming back to sampling in that sense.
Got it. Right.
Yeah.
I see. So yeah, so there's actually kind of two very similar sampling problems. One is there's a gigantic world out there of possible data you could collect to create the data that goes into your model for training and validation, and that like you make choices before you create your data set that gets used for training. You and a lot of that you end up having to sample. You have to simplify it down. You have to pick only a finite subset at the very least. And then the same problem kind of comes up then later when you need to validate your model, because you can't validate it on like all the possible data you could validate it on. So this same sort of problem of sampling comes up. And it would, yeah, I think one thing I've been trying to do is sort of keep an eye out for potential research topics, since I know a lot of folks in ML Collective are very research oriented. And it does seem like thinking more clearly through these kinds of sampling problems that have some similarities to what's come up in the past in statistics, but maybe look a little bit different when they're done at internet scale or on the kinds of data that companies work on, as opposed to clinical trials or other scientific enterprises. I think that's a place where somebody with like a statistical kind of background might be able to do some really impactful researcher work.
So the problem with the cameras sounds like you have the same problem as what Tesla has with their car cameras, where they have different cameras, and then each camera effectively has its own data distribution. So when you sample them all together, they're not the same camera, or maybe the angle is different. And what they've been doing is, you can see in some of their talks, they're tackling a couple of ways. One way is they're trying to normalize all their cameras images to put it through a neural network into, I think they call it like a synthetic camera. So they all go into one camera, and then out of that synthetic camera, you can use all the images and then put that into your neural network. The second thing they're doing is they're trying to calibrate their real life cameras to their model, like a software model camera, as much as possible in terms of brightness, contrast, pixel level. So I don't know if you have control to your cameras, but one way is to like only give your company's type of cameras out, or control the hardware, so that you can align your data closer. You might look into what Tesla tries to do. It seems like you have a similar problem.
Yeah, they definitely. I look for their talks for some inspiration, because they have a really hard problem and a lot of resources. So they definitely put out really good tips and tricks here and there, for sure.
Yeah, one other thing. Well, like I've seen people who work in robotics tackle this the most, because the form of their sampling seems to be like, the most complicated. And I've seen a lot of recommendations to like aggressively kind of simplify the signal, like project it down into an embedding space, or like use simpler sensors, just because you end up with something that's more robust. So sort of like maybe you might immediately think, oh, I want to run this robot on like 10 cameras pointing in different directions that all have like super high definition feeds, but then like you're now your machine learning algorithm can learn to depend on super like precise details of those cameras and of that information stream. And if you simplify it down to something like that's where a lot of extraneous information is sort of thrown away, you can end up more robust to distributional shifts, more robust to changes in the sampling, more robust to changes or degradation in the sensors. So sort of like trying to maybe make as much as you can out of a simpler signal can be one way to avoid these problems. All right, so there were also some nice sections. The section on labeling was one that I liked quite a bit. Just sort of talking about the different kinds of labels that you run into when you're doing machine learning out in the world, where most of what they're thinking of for machine learning, I think, in this book is like you have data about users, you have data about a system that you're running. And so like more like the like Google or Facebook or any business that's tracking user data, what they have. So these like labels by hand are maybe the most famous kind, the kind that most people think of, like that picture is of a bird, that text is toxic or not toxic. But also these like natural labels come up a lot more often in these systems with feedback, systems with interaction with users. So any thoughts or comments on the labeling section from anyone?
I stumbled on the programmatic labeling tool Snorkel after going through this section, especially the use of classifiers to label a more powerful classifier, where we can get weak supervision from either classifiers that are trained for a different task, or either classifiers that train with less data. And this, I tried out few experiments, and this already accelerated the annotation time that's taken by human labelers.
Awesome. So did you say Snorkel is the tool that you
Yeah,
use?
Snorkel.
Awesome. Yeah, so maybe for folks who like either skim this section or are less familiar with it, so this weak supervision idea is like there's lots and lots of heuristics and like simple computations that could be used to give like a really crappy classifier of our data. So the example they give is like if the word pneumonia appears in a doctor's note, then it's more likely to be an emergency. So it kind of draws some ideas from maybe like older machine learning or from like older forms of yeah, like good old fashioned AI with these like heuristics. And then the idea is that these can provide kind of like weak labels. They aren't perfect labels, but like weak labels to your machine learning system. I think Deepak was saying that they incorporated it into their labeling pipeline so that human labelers get maybe information from these weak labels, these labeling functions, and that allows them to move faster. Is that right, Deepak? Nice. Yeah. So this is something I haven't actually used Snorkel yet, but I've been hearing about it for a while, and it seems like a kind of cool, like a cool way of generating these weak labels. Like with natural language, there's lots of like people can come up with really good weak labels just by like thinking about it. Or like so you use things like regular expressions, like just checking for words, checking for substrings, like really simple stuff all the way up to like various like using various kinds of machine learning models. You could imagine actually like passing something as a prompt into a language model, looking at its outputs, and then using that to determine what the potential label might be. So all these things are ways to provide these kind of like weak labels. I think Aman had a comment here on wanting to know a little bit more about strengths and weaknesses of weak supervision. Aman, I think you're in the meeting if you want to comment on that.
Yeah, I mean, yeah, I think this section I was hoping for a bit more insight into, when does it work, what are the failure modes, and what do you do if it's not working as well. So that's yeah, I mean, I felt like that having that elaboration would make it more useful. This particular section.
Yeah. I think it's mostly just a pointer, which at least was helpful for Deepak to learn about this tool and the basics of how it might be used. Have you used anything like these weak supervision, weak labels, Aman?
I mean, I've used, distance supervision so I mean, not like a tool like Snorkel, but like I've used distance supervision to sort of label data in the past and use that, which is a kind of weak labeling. But yeah, I mean that's one of the reasons why I was hoping for more details, because then I would know, how much effort I need to put in to figure out Snorkel.
Yeah, it'd be great to know a little bit more about that. I would imagine like yeah, the Snorkel folks probably have their own like work about what claiming that it works for a bunch of use cases. It would be good to get like a little bit of the failure mode analysis. I don't know if they have that available.
They do have some statistics because those heuristics, they might be conflicting with each other and they might not cover the entire data set. So they wrote a wonderful statistics on coverage, conflicts, and agreement among these weak labelers. And then they also have a matrix manipulation where they combine all this weak labeled output and generate a probabilistic score for each data sample. That's kind of a weak signal on how certain the decision is.
Yeah, I think the main thing I think there's like a neat setup here. It's like it's more complicated than just like, oh, like throw in a couple of these things and it just like, I don't know, adds up their results or whatever. Um I think the question that Aman and I have is like, okay, does this work super well in practice? And basically everything breaks or runs into failures of some kind. And so it's good to know ahead of time what failures other people have run into, like, oh, my weak labels turned out to be way too confident, right? And then they were like, the Snorkel was telling me that the label was 90% spam when it shouldn't have been. And like when it should have been maybe more like 60%. And so like we consistently find that if you put in a bunch of labeling functions, it becomes really overconfident. Like that kind of or maybe it's the other way around, right? I'm just this is just like an example of a hypothetical off the top of my head. So like knowing a little bit about that can help you make the engineering decision of like, oh, well, false positives aren't bad for me. I actually care way more about false negatives. So overconfidence is fine. I'd be happy to use Snorkel if it's overconfident. Yeah, I liked the idea that these labeling functions are a way to take subject matter expertise and kind of like apply software engineering principles to them. Like that by writing down this subject matter expertise into a bunch of these little Python functions, like this one here, that you are kind of like that you're making a versionable, reusable, shareable, distributable version of your subject matter expertise. It's a cool idea and a different approach to the like machine learning takes subject matter expertise and like compiles it into the weights of a neural network or compiles it into the decision nodes of a decision tree. And it's cool to see a different approach for that with weak labels and labeling functions. Any other thoughts or questions about either weak labels or maybe other pieces of the labeling pipeline? Let's see. Oh yeah, we talked about different kinds of labels, how to get implicit feedback. The best labels are labels that arise naturally, that like from the machine learning model, like performing its task, it gets a label. Like you recommend something to a user, and then they either like it or they don't like it, and then you know whether they like clicked on it or didn't. That's like way better than something like diagnosing somebody with a disease. It's much harder to maybe get that feedback on whether you were right or not. So there's like a design kind of thing that's a little bit more on the like product engineering side and a little bit further away from ML engineering. But that if you incorporate that into your product design, then you can end up with a much better machine learning system, a fundamentally different one that has natural labels coming in continuously while it's working, so that you can set up something that looks more like continual learning for that system. Aman did also have a little bit of a criticism of the view of like recommender systems as having natural labels. I don't know if you wanted to talk about that, Aman.
Yeah, I mean, it does have natural labels, and I've worked on them before, and it's great for like learning, for the learning part. Like at least, I mean, recommended systems is a tricky thing. It doesn't fall very well into the, I mean, at least not neatly into the supervised learning paradigm, though that's what we try to fit it into. And so you can, so recommended systems, it's probably more like a reinforcement learning paradigm, but
Yeah.
that's not how you end up doing it. So what you do is you learn these affinities and functions or neural networks which represent affinities between objects and people and whatever you want to recommend. But yeah, so it's great for that. But the problem comes in evaluating, because you can evaluate these old affinities, but now if you're going to deploy a new recommender system, it's going to like essentially what people see is changing. So it's a non-IID setting in which you're going to test it. And so the only way to get actual final metric that you care about is by doing A/B testing. And so that was the only point I wanted to make.
Yeah, I think one other thing that I liked that I thought I saw in your comment was that because the algorithm is also choosing what to recommend, it like influences what data it sees, much like a reinforcement algorithm. By taking actions in the environment, changes which future samples it sees. And so you have this possibly vicious feedback cycle where
Right.
like you're only looking at data that the model thinks is interesting, and you have like an explore exploit trade-off, again coming from more this like reinforcement learning kind of world, where you have natural labels, sure, but you have an unnatural system for generating your data, for sampling that data.
Right. Yeah.
Yeah, natural labels maybe almost makes it sound like the problem is easy because it's got a naturality to it, but I don't think that's entirely the case. All right, there's more sections here on class imbalance, on data augmentation. Is anybody particularly interested in one of those, on class imbalance or augmentation or some particular sub piece there?
I've been trying to do some reading and some research into like synthetic data sets. So people either using things like copy paste in images or GANs or some sort of synthetic data set to train, I don't know, like image classifiers or something. And it's something that I haven't tried out, to see the experiment of does it actually help in the real world or in your actual universe where you're going to be doing predictions. I think it's maybe a little bit niche still, but it's something that I've been trying to speak, because I know there's other ways to get synthetic data in other kinds of problems. But I know that there's things where the positive label is really, really, really hard to come across. And I think that's kind of an interesting area of research to see, can you build synthetic data besides just, maybe left, right, augmentation or something like that, that could be interesting to look into.
Yeah, I think data synthesis is in some sense like dual to weak labeling, because if in general, your data synthesis is not like quite as good as the real world's data, and similarly, like your weak labels are not quite as good as whatever your ground truth label is. And in both cases, you're trying to come up with some good enough approximation that you can bootstrap like the process of getting a good machine learning model. So just as we can use sort of like regexes or like string manipulation things to do weak labeling of NLP. Interestingly, there's this example here is basically using basically a regex, an inverse regex, like a regular expression generator rather than a regular expression parser to get to do like find me a Vietnamese restaurant within 2 miles of my office, find me a Thai restaurant within 5 miles of my home. So like generating expressions from a regular language as opposed to checking whether it fits some regular language. So in general, I think there's like probably good opportunity for weak labeling and data synthesis methods to kind of like learn from each other and fit into a broader theory of like weak machine learning as an adjunct to like those sort of like stronger machine learning where you have really reliable data, really reliable labels that you want to learn from. Ooh, I'm on, what's this paper here?
Right. So there's this, I think, recent paper from MIT. I mean, it's like, basically the thesis of the paper is that, hey, GANs have gotten so good at generating stuff. So, I mean, how well can we use them? And apparently, like they're claiming pretty, I mean, good gains by using GANs to generate data and then using that for training. And yeah, I mean, I think there's definitely been progress in this direction of, how I mean, there are the companies built around it at this point, which basically generate data for your training. And then, I mean, hopefully over time, it just keeps getting better.
Yeah, definitely. And I think like, the same ideas that get used in sim to real in robotics, right? Like instead of calling it synthetic data in robotics, they call it like simulation to reality transfer, sim to real. And I think some of the lessons learned there about like, oh, actually, you like, because your data generation, your simulation process isn't really the real world, you actually maybe want to make it even more varied, right? Like in the Rubik's Cube work at OpenAI, like they didn't just use a physics simulator with the exact laws of physics, that we have, to the best of our knowledge. They did things like turn friction down, turn friction up, change the intensity of the lighting in different ways. Just like all kinds of additional variability so that you don't overfit to like particular weak features of your data of the like simulator. And similarly, like Vlad Kultun at Intel is like big on this, like do not don't use super precise sensors if you don't have a super precise data source. So similarly, you might want to like do a lot more fuzzing if you're using data synthesis than you would if you were using real data, and sort of like project stuff down, embed it, add a ton of like more data augmentation, like noise, than you would otherwise if you're using this kind of data to sort of like avoid overfitting. So yeah, I think there is a lot of work going on in these kinds of areas, but maybe not anything. Maybe what we're missing is a set of ideas to really draw it all together. Some like heuristic categories that say, here are some like general ideas and the general principles here that might be useful research or useful sort of review or explanatory content that people could work on.
Yeah, another thing that I think, and again, I think there's work around it, but it's like from a practitioner's point of view, if we are, if you're using generated data, I mean, one is quality, but also you probably need a lot of control. Like it needs to be controllable generation and like often very fine-grained control. And so, I mean, yeah, that is something also which would probably be needed, in that framework that you're talking about, to how to control the generation.
Yeah, which suggests that maybe, GANs and large language models are our like best generative models for images and text. They're also like infamously uncontrollable. So that's a tough one. The like trade off between the like flexibility and expressivity of the model and its controllability and your ability to make sure it's generating the kind of data you want.
Yeah, I have two comments about the GANs. I guess the first one is like a business perspective. Now you got to make a GANs that works and then check if that works. So it's almost like two problems. So GANs probably falls to the end of the ladder. And in terms of risk, it seems really risky. And then the second comment is, in this chapter, there was an example of the CycleGAN doing very well or helping out a CT scan segmentation, and I guess it was published in Nature. And the thought I had was, I never seen CycleGANs do well with or synthesized data do well, but I don't know much about GANs, but maybe it's good enough for grayscale segmentation. Because that's what the CT scan segmentation task is. Like maybe the CycleGAN is good enough for segmentation purposes. So that's I'll probably try that if I ever run into a grayscale segmentation problem.
Yeah, I think that definitely falls under this idea of like the more you like compress your data or the like less detailed your data is, the more coarse grained your data is, the more helpful these synthetic processes can be.
Yeah.
Right? Because in principle, like a CT scan, these like X-rays are, it's like this 2D compression of the like 3D information of the inside of the body. You could try to come up with like 3D MRI data that's like a point cloud, and then like maybe there's like lots and lots of channels that tell you about the density of different substances at different points in this 3D structure. But now, especially if you're trying to then synthesize that kind of data, that's way harder than synthesizing just the like projected version, right? So I think that's another win for this idea of like, if you move down to like a less fine-grained, less faithful data representation, maybe you can make more use of these like synthetic data approaches of different kinds.
Yeah, I also had a bit of a rant because I feel very strongly about it. Is the class imbalance problem? I mean, I feel it's an embarrassing problem to machine learning. Like it almost feels like you're not really doing machine learning. Like if you have that problem, but I mean, it's a fundamental problem. It doesn't really go. I mean, at least not learning. What one would call learning should not be this sensitive to class imbalance. And I mean, I put the rant there that when I first encountered it, I was like, this is just the wrong area for me to work in. This doesn't work. What are you talking about? And always, every time, I mean, I've faced it every time. I mean, not every time, but a lot of times, and all sorts of tricks that you have to just, keep trying and make it work. And feels like alchemy more than more than engineering. But yeah, so that's just something. But yeah, I guess it's very closely related to the sampling problem and all of that. But I mean, it's just any thoughts anyone has about it, I would love to know.
Well, one example that's, you could say it's balanced data. Although it has this issue, which is object detection. You could have a balanced data set of your output classes, but the bounding boxes are, in terms of the positive bounding box, where there's like an object in the bounding box, and the negative for no object in the bounding box, you can get an imbalance of predicted bounding boxes. Or I mean, that happens, and that's a big issue. And that's, if you want to do object detection, you got to figure out this bounding box imbalance problem, which is the same. I think of it as the same as this class imbalance problem. Very at the heart of this machine learning.
Right. And even, for instance, like even in NLP, like, entity direction, mostly your document does not have entities, and it's a hugely imbalanced problem.
Right.
Right.
Yeah, so you got to deal with it. It's not going away from it.
I know. I mean, yeah, I've learned to deal with it. But I mean, I do feel like, if there's a learning algorithm which handles this better, I would trust it a lot. Inherently does a better job of not getting such, like just get off track by just some statistical imbalance.
Yeah. I mean, I've dealt with this. I'm still dealing with this. I probably will deal with this forever, the class imbalance issue. I'll say my thoughts on it are, I think the oversampling technique, where you copy the minority classes to balance out the classes of the majority classes, I think that technique is not as useful as other techniques. I think that technique is probably fading away. Undersampling is probably not a good technique anymore compared to what's modern. I think what I found most useful is the focal loss, which is in the chapter where it was published in 2017, where they had this bounding box object detection and bounding box imbalance issues, and they don't describe. It's not well described in this chapter, but this loss is like, I think this was like a step change in object detection, this function, and they don't describe it well in the chapter, but the problem with the object detection, or just problem in general, was if you have a lot of correct predictions, so you have like 1,000,000 correct predictions, but you sum up those losses of the 1,000,000 predictions, that sum is a loss, and that could outweigh the losses of your incorrect predictions. In when you're doing like a vanilla machine learning, and that's a big issue. Like now you can't really learn the wrong classes because you have so many correct predictions that those overshadow your wrong predictions. And what this focal loss does is, on the picture, on the y-axis is the loss for, like, say, a prediction, and then the x-axis is the probability of a ground truth, so 0 to 1. And one's like a correct guess. If you're close to 1, you effectively give that correct prediction a lower, you lower the loss of that. So if it's like at 1, it gets like a 0 loss. This focal loss, it makes your correct predictions contribute less to the final cost function. And I think that's like a very powerful idea.
Yeah, I came across focal loss when looking at object detection stuff, and like it seemed to me to be kind of like a hacky thing that people had found worked. I didn't realize it had this like nice interpretation in terms of class imbalance, because when you do dense object detection with something like YOLO type methods, you like guess a bounding box for every like tiny little piece of the image, and then most of them end up having nothing in them. So object detection ends up with this really gnarly class imbalance when framed that way, and focal loss is an important part to like address that. But that means that it's not just a thing for these object detection methods. It's also something for other places where you have this class imbalance. And yeah, Daniel's interpretation there, in terms of like down weighting when you're getting things right and up weighting when you're getting things wrong, like helps explain like how it makes it easier to learn. It's like the cross entropy, but with this like exponential weighting term that down weights things that you're doing well on. So it probably has some like elegant information theoretic interpretation, where you can connect it to like Renyi entropies or these other sort of like exotic ways of thinking about entropy and surprise. But so it'd be great to see if anybody like knows work on that, or wants to think about it and report back to see if there's like a good mathematical interpretation here. But it's it is what people found empirically to help a ton with class imbalance. Does anybody use like oversampling or undersampling, like throwing out data from the majority class or oversampling stuff from the minority class?
Yeah, I've done it all. And it seems like Chicago over the years, they eventually just go to some version of focal loss. It seems like they just leave the data as is without oversampling or undersampling, and they just change the loss function. And that kind of shifts the class imbalance problem from your training data to your learning algorithm. That's the trend. From my experience, that seems to work the most efficient from what I've done.
It's tricky to synthesize. Like oversampling, you want to be able to synthesize new data. And so you get back to the same problems that we had in our synthetic data section. Maybe there's a lot more conditional sampling here, where it's like, given an existing minority class data point, can I generate transformations of it? So then it's like, it's not pure synthetic data. It's like conditional generation, or even like data augmentation of that minority class. I know the PyTorch book by Viaman and others does a like CT scanning data set. They do oversampling of the minority class. If you want to see like a thoroughly worked out example on how to use these methods. But yeah, good to know, Daniel, that people out there doing stuff tend not to use it that much. Oh yeah, go ahead, read one.
Yeah, I just wanted to know that sometimes it might not just be the minority class that needs to be oversampled. Okay, from my experience in NLP, even in developing name entity recognition, I've had a model that was able to extract data entities from documents. However, there was something lacking. It couldn't extract some certain formats. So sometimes you need to introduce those formats, maybe using heuristic method or just manually duplicating documents, introducing those formats manually so that the model can actually learn from them. So sometimes you might even have balanced data sets, but still you need to oversample to account for some changes, some minor changes in the distribution of characters in the documents.
Interesting. So I lost a little bit of what you were saying there. You cut out a little bit during some important parts, but it sounded like you were saying that you needed to oversample the minority class because it had slightly different like characters and content in the document. Is that what you were saying?
Yes, exactly. Like for example, date formats. You know, we have several date formats. Some of them are present in the document in the training data set, but in production, the model is going to meet several other formats. So you need to sometimes introduce those formats manually.
I see. Yeah, yeah. So I think in general, there's a lot of overlap. So like synthetic data solves this general problem of like, I just don't have enough data like to train my algorithm at all. As Ruwan was saying, there's like a lot of utility for those like synthetic data sets to solve the like narrower problem of I don't have enough samples from my minority class. Because it's sort of like it's the same problem of like not having enough data, but now it's narrowed down to a particular component. And then also just in general, like being able, if you know things about the differences between your production set and your training set, your test set and your training set, then like this kind of oversampling and augmentation can really help bridge that gap if you do it right. But yeah, the tricky part is being sure that your augmentation, synthesis, oversampling actually is reflective of the real data that you're going to encounter.
Oh, I should clarify my statement earlier about the focal loss and sampling, oversampling, undersampling. My comments were based only on computer vision, so I don't know how my comments apply to NLP. My comments only refer to computer vision.
Right. So I mean, yeah, I think just to add on to that, like, I think I didn't want to derail this discussion into more about focal loss because I mean, for me, when I encountered, like, I looked up focal loss but I was working on an NLP problem, and so I was trying to. I mean, one question was how do you tune this hyperparameter, and like and I couldn't find much on it, so I was gonna ping you and ask you, okay, how did you use it for NLP?
Yeah, I'd be interested, yeah, definitely in more rigorous approaches to figuring out what that gamma should be, maybe, yeah, on the basis of like information theoretic ideas. And that might help you transfer ideas from computer vision to NLP if you can characterize those information theoretic quantities of like, relative relative levels of these different classes. Actually, there's one more thing about synthetic data that I wanted to mention. There's like two examples of synthetic data that I've been working with recently that I thought were really cool. One was a receipt data set. You want customers to be able to like take a picture of a receipt and then get out everything that was on the receipt, their like the price of it, the name of the item. And because that's a relatively constrained data set, they were able to make this group was able to make a really good renderer of crumpled receipts that just like could take into account lighting things and 3D deformation. And then like the content of the receipt is relatively structured because, receipts are generated by machines. So they were able to make this really beautiful synthetic receipt data set. And it was really inspiring in terms of like, oh yeah, if you have the right problem and you really, really understand it, then the data synthesis, you go really far with it. And they were able to make a really, really good optical character recognition and information extraction tool for receipts on the basis of data synthesis. And something similar with full stack deep learning, the like class, all the experiments are done to like extract handwritten text from images. There's a data set of actual handwritten text that's involved there, but most of the training starts with this like kind of pre-training on synthetic data by taking a text data set, a real existing text data set, and then grabbing characters from MNIST type data sets and using like images of single characters and data about like language and how you create sentences out of single characters to make images of whole text. And that's super important for making this system work. This kind of like bootstrapping to get more data is super important for that, for the text recognizer. And so it's both of those were really like, I was a little skeptical of data synthesis until I saw those two examples and saw how powerful they were. So it does seem like a really something to at least, spend a day or two chin scratching about when you approach a new problem. Can you come up with a really elegant way to do data synthesis with the right, conditioning on the right information?
I was just going to say one quick comment here about the data synthesis. This is where I think like the full stack deep learning approach and like the MLOps approach to making a model better is really important, because if you understand where your model is failing, then you can focus your efforts into where and how you need to do this data synthesis. I mean, I know it comes back to like the data flywheel and the full cycle of understanding your error analysis and figuring out where to best put your efforts into it. But I know we talked about Snorkel a little bit ago, and they have some like powerful slicing tools that could help kind of focus where people spend time in data synthesis and data augmentation. I like how that the full cycle keeps popping its head.
Yeah.
When you talk about stuff like this.
Yeah, it is hard to like focus in on any particular component, which makes it a really tough engineering problem, because engineering proceeds most effectively when you can modularize, separate things out, and then work hard in one area and only and with confidence that you're helping everywhere else. But yeah, it does seem like in ML systems, it's really difficult to avoid connecting all the pieces being connected to each other, which is maybe also not so dissimilar from other really large distributed systems. There's a lot of like interplay between the assumptions of every single database technology that you're using in a data engineering stack. Lots of complex dependencies. So it's tough engineering problems in both cases. Juan Pablo mentioned the like full stack deep learning, more ideas from that class. There's like a somewhat fictionalized self-driving car example where the images that cause the self-driving car to miss pedestrians are ones where there's reflections off of the windshield. So like the lighting angle is such that you end up with a reflection off of the windshield. And the suggestion there is to try and synthesize more reflections. If you can narrow down through slicing your data to these like specific types of failure modes of your model, then you can get to those like slightly easier data synthesis problems, and maybe hand it off to an expert in graphics and rendering, or in NLP, hand it off to a language generation model that's able to generate these other kinds of examples.
To add on to that, if you're working on something that's like a self-driving, this is when the Tesla talk, self-driving car. You have, it seems like you have to create, you have to data synthesize and create a simulator that emulates the world, because so their data distribution has like a long tail distribution where you have some really critical events that they want to prevent. But the dilemma Andre was talking about is the better their model gets, the less of these real life events you're going to see. But how are you going to train on these events that you're never going to see? You have to create a simulator that can create these events for you. Otherwise, you're going to be too late, and it's going to happen in real life, and it doesn't even happen that much.
Yeah.
So there seems to be a push for now real simulators of the world so that they can create these long tail distribution cases.
There's some actually interesting work in computational cognitive science on humans have like a heuristic bias towards really unlikely but really unpleasant outcomes. Like when we go to the beach, we fear being eaten by sharks, even though like that only happens to like 10 people a year out of all the people who go to the beach. And there is an accounting of it in terms of like wanting to sample from that rare part of the distribution, because even though it is rare, it has a substantial contribution to the loss. Nassim Nicholas Taleb, in his book Black Swan, like talks a lot about how these, if you take an expectation and calculate like an average loss and while you're trying to figure out your risk exposure, these long tail events tend to dominate the calculation of that expectation. The same thing shows up in statistical physics in calculations of free energy. It's actually the rare events that contribute to that expected value. And so there's something to be said for trying to oversample those things. In statistical physics, there's methods for that. There's like transformations that people do to sample more from those rare areas and then mathematically be able to calculate what the true expectation was, even though they sampled from rare things. And similarly, in cognitive science, it's clear that human cognition relies on these same things. I've never had to actually, respond to a situation where I have no pants on and I'm giving a presentation, but I've dreamed about it enough that I think I have a good playbook in case it ever happens. So similarly, our models maybe need these synthetic dreams of what would happen if they were about to hit somebody, and that's way better than waiting for them to sample an actual case where they hit somebody. Oh, it's also 10 o'clock. Thanks everybody for comments and discussion on this one. The next chapter, I should have it from Chip later today, so I don't have it ready for you yet, but it's either going to be on feature engineering or on model development. And I'll post it in the Discord, put it up on the Notion doc, and we can read it and talk about it next week.